welcome to another video. So I broke down and purchased an oscilloscope. It's a Siglent, something like SDS 1052. It was the cheapest oscilloscope I could find. Cheap oscilloscope for a cheap person. But the thinking is also, like I did with 3D printers, is go with the best name that's really cheap that you can find. And then once you have your toes in the pool, you can figure out, all right, I'd like to do this a little bit better. But I've never used an oscilloscope yet, and so I have this, and that's what's different about this video is I have no idea what I'm doing. And that'll actually, I think, make it more expert, because I'll run into the same problems that other people run into. I mean, in some ways that's true, rather than, here's the fast Fourier transform button. It's just how do you, as the Ferengi said to Engineer LaForge in Star Trek, when they captured a bunch of technology and they had no idea what to do with it. So, make it go. So that's what this video is about, is can I make an oscilloscope go? And so let's get to it. So one thing I notice right off the bat is it's fairly light, which is nice. And I'll get it out of this and see what else we got in the box. So here it is out of the box, and this is everything that came with it. So there's not a lot. It's got a nice little handle there, and it's got, like the things on your keyboard. It's got some things here so that it is up like that, and didn't come with a manual. That's not good. Now I've just set the scope up over here, which I think will be a decent place for it. It's actually very light, so I think it'll be okay there. It might block the airflow a little bit. I'm not taxing the power supply. The only other thing that came in the box was two of these. And these, as they label them, are the oscilloscope probes. So when you open that up, you get another little user guide, you get this bag, and you get your probe. So there's already something that I had wrong, and I think I've got it. I understand it now. But this is like a little coaxial connector that will plug in, say, for channel 1. And I thought that was going to be the negative return there. But I guess the way this works is this is actually going to be the negative. So you'll hook this to your negative like you would with a multimeter. And then, if I can show it, if you pull back on this, you get a little fish hook. And then it's spring-loaded. So you put that on what you're measuring. So I think I understand that. And then it's got a little toggle here. If I can show it, the lighting's not that great. But on one side of the switch it says 1x, and then it's down there on 10x. So you could move it there, 1x or 10x. The 10x is, I believe, a 10 mega ohm resistor, and this is a 1 mega ohm. So I'm going to use the 10 mega ohm resistor, which I think is what's most commonly used. So the next part of this is apparently the first time you use these probes with the scope, you need to calibrate them. That's not actually the word they use. Frequency compensation. And so what you do is you hook the negative up to the negative there, and you hook your probe up to there, and when you press one of these buttons, it just puts out a reference square wave, and it should be square. Now if it's not square, what you do, if you can see it there, is there's a little screw, and they were nice enough that they actually gave a little tool to adjust that screw. That's what this thing is. And as I understand it, that tool, that screw is adjusting a variable capacitor. So that's the first thing we want to do. Let's see if we can get that to work. And then there's just some other, I mean, these are just to color code things, and then I think these yellow things are to potentially protect the tip or stabilize the tip or something like that. But that's the first thing. So let's try and get that done. So this part they do actually cover in the quick setup that's provided. So the first thing is just turn the thing on and see what it does. It's got some lights that have come on. Here's some relay switching. That's nice. That's promising. And the first thing they say to do is to press the default setup button to restore the default settings. So default setup. Now if we look down here, we've got this thing, and that goes to ground, and then this, if I can get a shot of it, it says 1 kilohertz, and it's a picture of a square wave. So we want to connect the ground of the probe to that ground and the signal to there. Then we're supposed to press the button auto. I hope this doesn't blow up. All right. So now we have our square wave, and it looks a bit funky. And they even show this to you on the next page, probe compensation. So we have it hooked up there, and it's putting out the square wave. And it should look like this one. That's undercompensated. This is overcompensated. So it looks like it's overcompensated. So now what I want to do is use this tool to make this thing a good square wave. And what I'm wondering now is whether I can do that while it's hooked up. What I'm afraid of is if those two things like bridge this and the thing, but it's probably worth a try. Okay, so I just used this little tool in there and fiddled around with that, and now our square wave looks like that, which I think looks pretty darn good if you ask me. Not that I know anything about this. So what I'm going to do now is just do the same thing with the other probe on the, I think I can get away with doing it on the other channel unless the reference only goes out to one channel, to make sure I've got two good probes ready to go. So I got the second probe compensated. It's a little bit tougher than the last one because the screw there was sort of stuck. I was worried it was stripped, but it was just with the included tool, it was kind of hard to get it going. So I just unplugged everything from the machine and used a traditional screwdriver to get it going. And then once it was in its operating range, you could use the other tool. And so now we have two calibrated probes. So now we get to the make it go part, you know. I mean, look at all these buttons and dials and, you know, what do we do? I guess even before, I mean, depending on how we want to go with this, I mean, why would you use an oscilloscope to start with? Why not just use a multimeter? Now, the thing that's cool about this, like let's say you have a small capacitor at 10 volts and you hook a multimeter up, and then you put the capacitor across like a 10 ohm resistor. By the time that the multimeter registers anything, the cap's at 0. So it'll just read 0. And similarly, if you have a alternating current going between like 10 and -10, it'll just say 0 on the DC sampling, and on the AC it will look for the root mean square value. What this thing does is it samples the voltage, I want to say 1,000,000 times a second, and I don't think that's inaccurate. I think it's sampling the voltage 1,000,000 times a second. The other thing that's nice is it's a 10 mega ohm probe, whereas most of your multimeters, it's 1 mega ohm. So this is also less intrusive for your measurements. And since you're sampling things 1,000,000 times a second, now you can see curves Now you can see oscillations and curves. So a multimeter allows you to see the pattern of the change in voltage over time, and that's why you use it. Now, I'm avoiding the make it go part. The quick start guide doesn't tell us a darn thing. However, don't fear, because if you put that into a search engine, it brings up a manual, and let's look at that. So here's the manual for this SDS 1000X series. We have the 52DL of digital oscilloscopes, and the first thing you can see is it's 204 pages, so thank heavens, because I need the information. And all we had before was the quick start, and then it goes through all of these. And one thing is that this covers a number of models. So like if we get down to the bottom here, I was looking, oh, this thing's got an arbitrary waveform generator. No, it doesn't. And like the cheapest one of those is going to be like $600. This thing was, I think, $260, maybe $265. I probably should have started with that, as well as why you want an oscilloscope to start with. So the main things here are the like I know, but the vertical, the horizontal, those are your two that and the Fetzer valve. Sorry. So in a minute we'll go back to just seeing if we can do anything with this, but just like there's this math button, and I've got the math button. This isn't an arbitrary function generator, but I've got somewhere on there is the math button, and it provides for addition, subtraction, multiplication, FFT, fast Fourier transform. I have no idea what that is. Differentials, I know what that is. Integral and square roots. I've actually wanted to have an integral of a changing voltage, and that's going to be the topic of a future video. But it's sort of like if you're discharging, like say, a cap into a coil. Not discharging a cap into a coil. If you're to heck with it, I'll cover it in a different video. I don't want to go off topic here too much. But what I'm saying is, like, this thing, to really use this thing well is it's not an elementary school kind of thing. It's a graduate school kind of thing. But can we just use it at all? So from what I gather, there's basically two things going on here. You got this button, and this horizontal button is adjusting the time frame that you're seeing on here. And then your vertical button is adjusting the voltage. So if all that's true, let's see if we can actually sample something and get it on there and see that it works. So what do we do? We'll take an Arduino, and we'll write a tiny little program on the Arduino to turn a channel on and off. So the output should look a lot like a square wave. Now we don't want to run it at exactly 1 kilohertz with 50% duty cycle, because then it would be like, well, maybe you're just seeing the this thing that you use for calibration and initialization. So let's go with like a 25 or a 33% duty cycle, and there's no reason to go fast. Let's, instead of 1 kilohertz, let's, I don't know, like 500 hertz or something like that. So let's throw something together. So here I had an Arduino board lying around, and I hope that it's not fried. I guess we'll find out. And what I've done is I just hooked a line here into the Arduino ground, and I've hooked the other line there into pin 9. So I have this program called Blink All Pins, and let's save it as oscilloscope test. Now let's get rid of everything except for pin 9. So right now this turns pin 9 high for 1000 milliseconds, or a second, and then it turns it off for a second. So let's turn it on for 2 1,000ths of a second and off for 8. So I guess that would be a duty cycle of, would that be 20% or 25%? I don't know. I guess it would be 20%. And 2. So this will be running at 100 hertz with the duty cycle of 20%. And it should be a square wave. So let's hook it up. Let's compile it and hook up the probes and see what we see on the oscilloscope. Okay, here's what I see. I have no idea if that's good or bad or if I've like broken the machine. I do like here it's saying 100 hertz. Didn't we just say it's 100 hertz? So let's just start fiddling around with dials. Oh, what's going on? Let's stop beeping at me. I was turning it the wrong way. Oh, baby. Yeah. Now let's turn the other knob. This is getting fun. No, that's got to be wrong. Yeah, that's good. That's good. That was better. Okay, and when we turn the vertical knob, that's adjusting the voltage on the y-axis. So, a little bigger. There. And somewhere it'll tell us the voltage. So this is just really cool. I mean, that's not the test wave. That's the wave coming from the Arduino, and we can tell because of the duty cycle, and it's saying that it's 99.8 hertz. And not to like geek out completely, but it's probably not 100 hertz because the digital write function call has like 4 or 5 lines of machine code, and you get it, closer to 100 hertz if you wrote it in machine code. So I think another cool button to press on this is measure. Let's see what it does. It didn't do anything. Voltage, measure voltage. Yeah, just do something. Oh, look at that. Look at that. See why I'm saying this is going to take a while. Okay, and then this knob moves it around. The universal knob. So what do we, I'm interested in Vmax. Make that go. So somewhere it should tell me Vmax, but it's not. Let's see if we can just zoom in a little with this is the time scale. No, that's the wrong way. Yeah, look at that. That's beautiful. That's just beautiful. Okay, let's just do one last thing and then we'll wrap the video up. But let's put an inductor across the pin in the ground. Let's see what happens. So now we have the inductor, and when I press that there, then the pin's going across the inductor. So now, well, see, you go like that. So now, boom. See how the waveform changes? Don't press it. Boom, because that's the inductor there. And that's like an inductive spike. So that's really cool. Okay, so I think that about covers it. That's how you take the thing out of the box, set it up, get it calibrated, and get it running to where you're measuring something. Now, there's going to be a lot that I have to learn to take full advantage of all of the capabilities of this scope. But one of the things I'm thinking going forward for future videos is I have an oscilloscope, so you probably want to look at some circuits that oscillate. And there's lots of those. You got your Hartley oscillator, you got your Colpitts oscillator, you got your Royce oscillator, you got your Joule Thief oscillator. I think the first one I'll start with is the 2-transistor oscillator of Forrest Mims. And if anyone got into electronics the same way I did, Forrest Mims wrote the book in the Radio Shack, Introduction to Electronics. So I think it'll be fun to build a bunch of oscillator circuits and put them on the oscilloscope going forward. But I can tell already that this is going to be a very useful tool. Very useful tool. Okay. Thanks, everyone. Stay healthy, and talk at you later. Bye-bye.